Hello, this video is to show you how to implement your controller designs that you designed using MATLAB for the SJ Servo. It is assumed by now that you have already done the MATLAB session, designed a controller to meet the objective of 50 radians per second for the undamped natural frequency and a damping constant of 0.6. For this video I'm using a proportional plus derivative controller with a gain of 0.005 and a zero position, an alpha value of 70. Before we implement the controller, it's a good idea to do a closed loop response without the controller, so that you can see just how good your controller is, how much improvement you've made. When you actually run the controller, you should find the output shaft moves backwards and forwards. Perhaps it doesn't show up fairly well on this video. However, if we look at the actual graph from the chart recorder plugged into the output shaft, you can see that the overshoot is pretty lousy. In fact, so bad that the oscillations haven't completed before the next step has come. So we can now go on to implementing our controller. Unfortunately, a proportional plus derivative controller can't be implemented directly. We effectively cheat. We put in a resistor capacitor network to implement this K into S plus alpha over S plus beta. But we choose the beta in such a way that it's really not going to affect the performance very much. To make life easier, if we make the gain K equal to our desired value, KD times beta, and force that to be equal to 1, then effectively we can choose a value of beta, and in my case that works out as being 200. By doing that, the pole is down at minus 200, has very little effect on the time response. In implementing the RC network, we need to work out values for the resistors and capacitors. So alpha was equal to 70, and if we choose a value for a capacitor equal to 5 microfarads, which is what I suggested in the instructions, we get a value for the first resistor to be 2.86 kilo ohms. Rearranging the equation for the beta value, we get a value for the second resistor to be 1.5 kilo ohms. So take our three components, two resistor boxes and a capacitor. Start by setting the capacitor to our 5 microfarads by adding the switches together. It's also worth making sure that all the other switches are definitely off. We can then set the first resistor value to 2.86 kilo ohms, again adding the different switches together. And finally the R2, again 1.5 kilo ohms. We can now patch this RC network in between the points 3 and 4 on our diagram. It's important you make sure you take out the connection between them. So following the wiring diagram, first of all we can go into the capacitor, and then in parallel with the capacitor we can put the first resistor, R1. We can then come out of the first resistor to the second resistor, remembering to make sure you put the bottom of the second resistor to earth before going back into the equipment at point 4. Now when we actually look at the output response, we see a lot less overshoot. Indeed, if we look at the time response, you can see it settles down very nicely, not anything like the amount of overshoot we had before. To prove the point, let's do some analysis on our graph. If you start by measuring the overshoot, which I made 33%, put it into the formula that you had for part A of the SJ Servo assignment, and out comes a value for the damping constant of 0.33. That's pure coincidence, it's the same as the overshoot. We can also work out the undamped natural frequency, again using the formulas from part A of the SJ Servo assignment. Let's assume T max came out as 0.05 seconds. Admittedly, it's not so easy to measure that accurately off this graph, but that gives us an undamped natural frequency of 66 radians a second. Of course, what we've seen is very different from our objective. We've definitely made an improvement, but there's a lot of sources of error that stop us getting a perfect response. To start with, the parameters that we used to get the transfer function came from an experiment in part A. I did give many of you alternative values to use, but nevertheless it's still come from experimental data. So we could have been designing a controller that wasn't quite for the box we thought it was. When you were implementing the resistors and capacitors, you might have noticed that there is a tolerance of 1% on the resistor values, 5% on the capacitor. Could be very significant. But even if that was all correct, we still wouldn't have got perfect results, because the formulas that we used that came from part A of the SJ Servo assignment were actually for a perfect second order system. We have now introduced a PD controller that stops it being a perfect second order system. More importantly, we had to use an approximation which put a third pole onto the system, and although it shouldn't have too much effect, it's going to have some effect. So our conclusions are that whilst we wanted a zeta of 0.6, we actually got 0.33, and while we wanted an omega n of 50 radians a second, we actually got 66 radians a second. What that effectively means is that the response is actually faster than perhaps we wanted. Remember, omega n governs speed of response, whereas we've got slightly more overshoot than the desired.